Okay, this is a Chapter 8 packet on hypothesis testing for population proportions. And just a quick note, again, we reference essential statistics, exploring the world through data throughout this packet. All right, this video is going to cover sections 8.1 and 8.2, the essential ingredients of hypothesis testing and hypothesis testing in 4 steps. All right, so in Chapter 7, we learned that confidence intervals are a type of statistical inference that can be used to estimate parameters based on the results of a sample. The margin of error for these intervals allowed us to quantify how confident we were in these estimates. So our confidence interval took our sample result, p hat, and added and subtracted a couple of standard errors or your margin of error. So we'll say plus the margin of error here, plus or minus the margin of error. In Chapter 8, we're going to learn how to use hypothesis tests to make a decision about whether it is likely that a population parameter is equal to a hypothesized value. So in each of the following cases, a person is interested in making a decision about the value of a population parameter. Okay, so the first one, a researcher is interested in testing whether new medical treatment is effective at increasing the survival rate for a disease. Second one, a pollster is interested in whether the public support for a candidate has decreased after a recent scandal. And the last one, a gambler wants to know whether or not the dice being used at a local casino are fair. So hypothesis testing is another type of statistical inference that will help us choose between 2 claims made about a population parameter. And so if we look at that first one up here, the researcher wants to know, is looking at whether or not the new medical treatment is either effective or not effective. If you look at the pollster one, the public support for a candidate has either decreased or stayed the same. So the pollster is interested in. Okay, and the third one, the gambler. The gambler wants to know whether the dice are fair or biased. Biased would mean unfair. So these decisions will be based upon a sample statistic. And so given that statistics vary from sample to sample, the decisions we make regarding these parameters are uncertain. So how do we make these decisions? How do we know if we've made the right decision? And what's the probability that we make the wrong decision? Hypothesis testing provides a method for making these decisions and allows us to control the probability of making certain types of mistakes, the chance that we make the wrong decision. Right, so we're going to use an example to illustrate the 4 steps in the hypothesis test. How can we test whether the die we are rolling is fair? So your first step, step 1, is to state a hypothesis about a population parameter. It's a claim about the world, and an alternative hypothesis. So we start with the null hypothesis, which is denoted by H with a subscript of 0, so H naught or H0, which is a status quo, excuse me, or prevailing viewpoint about a population parameter and states that the parameter of interest is equal to a specific value. So in our case, the 6-sided die that I have in my hands is a fair die. This means that the number 6 is just as likely to be rolled as any of the other 5 numbers. In other words, 1/6 of my rolls will result in a 6. So this is my null hypothesis. We can also express this hypothesis using symbols. So my null hypothesis is that the proportion of 6s that I get is 1/6. So P is 1/6. And this number right here is often referred to as P with a subscript of 0. That's to remind us that we're using the proportion from the null hypothesis. So we'll see that in some later calculations. Right. The alternative hypothesis then is denoted with the capital H, subscript of A, so HA, which is an alternative to the null hypothesis, the change in the population parameter that the researcher hopes is true. So in our example, this is that the 6-sided die that I have in my hands is not a fair die. The 6 does not appear the same proportion of times as the other 5 numbers. So we can express this hypothesis using symbols as well. So in this case, we're saying that P is not 1/6. And so looking at these 2 hypotheses, again, our null hypothesis is that we have a fair die, and we get 1/6 of our rolls are 6s. And an alternative is that it's not a fair die, that we do not get 1/6 of our rolls ending up as 6s. So notice that there are no overlap between these 2 hypotheses. So any number I get, any proportion of 6s that I get is either going to be 1/6 or it's going to be something else. And so keep in mind that these hypotheses must be specified before the sample data are collected. So they are your first step. Right. A significance test is designed to assess the strength of evidence against the null hypothesis, and we will assume that the null hypothesis is true until we collect enough evidence to suggest otherwise. So in our case, we're going to assume the die is fair until we collect enough evidence to suggest that it is not fair. And a hypothesis test is similar to how our justice system works. You assume the defendant is innocent, that's your null hypothesis, until there is enough evidence to conclude otherwise, your alternative hypothesis. One last comment about hypotheses, your first step. Keep in mind, this is something technology is not going to be able to do for you. It requires an understanding of the context of the problem. So writing these hypotheses is going to be up to us. All right, step 2, determine how you will use data to make your decision. Step 2 also involves choosing a significance level, and we're going to learn more about this in a later piece of this example. So assuming the die is fair, we know that our samples of rolls will typically result in a 6 around 1/6 of the time, give or take some variability. So how much variability? We can use the central limit theorem to create a sampling distribution for the proportion of 6s and a random sample of 60 rolls of a die if the following conditions are satisfied. So our first condition, and these are the same conditions we've seen in earlier sections. First condition is the sample random. So we're doing a random sample of 60 rolls of a die, so we can say this is yes. Is each observation or roll of the die independent? We can say yes. We can assume that if I roll the die the first time and get a 5, that's not going to have any impact on my second roll. So the rolls are independent. All right, condition number 2, we're doing 60 rolls. So our sample size is 60. So we want to see if that's a large enough sample size. So we need to check by using those same formulas we had earlier. So your sample size times p, see if that's greater than or equal to 10. And our sample size times 1 minus p should also be greater than or equal to 10. Since we don't have our population proportion, we turn to our null hypothesis. And remember, we're assuming this is true until we get evidence to suggest otherwise. So we're doing the sample size times our hypothesized value. Right? So we're going to do 60 times 1/6. We get 10. We've got to do 60 times 1 minus 1/6, which is 50. So we can say yes, the second condition has been met. And that's why our sample size is large enough. And then the third condition is the population large enough. And we're going to use the same check we had earlier. See if our population is at least 10 times bigger than our sample size. So is n, capital N, greater than or equal to 10 times 60, which is 600? We can say yes. We definitely have more than 600 rolls. There are an infinite number of rolls. An infinite number of rolls that we could do. So again, we can say this third condition has been met. And so step 3, since all 3 conditions for the central limit theorem have been met, we can create a model for the sampling distribution for p hat. So remember, we're assuming the die is fair until we have evidence to suggest otherwise. So that means our sampling distribution for p hat is going to be approximately normal. It's going to be centered at or have a mean equal to our hypothesized value, which is 1/6. And our standard error or spread is going to be a very similar formula to what we used earlier, but notice it's got p with the subscript of 0 in there. Remind us that we are still assuming the null hypothesis is correct. So we're going to replace p with that subscript of 0 with 1/6. And our sample size is 60. And I'll leave this up to you to verify with your calculators. You should press pause and try this out on your own. So you get a standard error of 0.048, about 4.8%. Right, so taking all this together, we can complete a sketch of the sampling distribution of the sample proportion of 6s when a fair die is rolled 60 times. So our sampling distribution of p hat, if the die is fair, should have this normal shape. So it's got that mound shape, single peak in the middle. Should be centered at 1/6, which is about 0.17. I'm going to change that to a decimal to make my next few calculations a little bit easier. 1 standard error above, 2 standard errors above, 3, and then go to the left as well. And we can put some numbers on the axes to see what we might expect. So if I add one standard error to our center value, we get 0.218. Just a reminder, our standard error was 0.048. It's from the previous page. So if I add that again, I'm going to get 0.266. And one more time, I get 0.314. And over on the left, if I subtract, one standard error below is 0.122, two standard errors below, three standard errors below. Keep in mind that the horizontal axis is showing us potential values of our sample proportion, or what proportion of 6s we might get if our die is fair. And so next part of this, we're going to roll a die 60 times and calculate the proportion of rolls that result in a 6. So note, if you're doing this activity at home, you can use the dice roller at www.random.org to roll 60 dice at once. Or if you have a die lying around, try rolling it 60 times, see what you get. What you want to do is calculate the proportion of your 60 rolls that result in a 6. So your p-hat may be different than mine, but I'm going to give you my results. I rolled it 60 times. I had 14 6s. So 14 out of 60 gave me a proportion of 0.233. So again, this is a p-hat. This is one sample result. All right, so next step, I don't know if that's evidence or not, enough evidence. So where is it in our distribution? 0.233 is somewhere in here. Here's my p-hat, roughly. So we want to know where that is relative to the center of the distribution. So we're going to calculate what's called a test statistic. So this test statistic compares the value of your p-hat with the value that the null hypothesis says we should see, and p0. And we're doing this in terms of standard units. So we're calculating a z-score. This is here to remind us it's for what we just observed. So we're going to take our p-hat, and again, I'm going to use mine in my example. You can use yours. And I'm going to subtract the center of the distribution, 0.17, and I'm going to divide by the standard error, 0.048. And this gives me a z-score of 1.31. Okay. So that tells me a little more than one standard error above the center of the distribution. Right, so next step, calculate the probability of getting a sample result this extreme or more extreme. This is referred to as a p-value. So our p-value is going to equal 2 times the probability that we get a p-hat as extreme or more extreme than our sample proportion. So I need to first figure out what's the probability of getting a z-score more extreme than 1.31. Right, so using the chart in the back of your book, I find that that probability is 0.0951. And that means I'm going to now double this. And we'll talk more about why it gets doubled in just a moment. So I'm doing 2 times 0.0951, and I get 0.1902. So this is the chance, or the probability that I get a result this extreme or more extreme if the die is fair. Right, so this p-value is the probability, again, assuming the null hypothesis is true, of obtaining a test statistic at least as extreme as the one actually observed. Extreme means in the direction of the alternative hypothesis. So remember, all our alternative hypothesis said that p was not 1/6. So since our alternative hypothesis did not specify direction, we need to look at sample results that are as extreme as the one we found in both tails of the standard normal distribution. So if I go back up to our graph, here's our p-hat, 0.233. So anything more extreme than that is in this tail. But we also have to look at the p-hats down here that are just as extreme or more extreme in this direction. So our p-value is taking this area plus this area. So we're doubling it. And so again, here's why we're multiplying by 2, because we're doing both tails for this distribution. Okay, so we're going to mark the location of our test statistic on the following standard normal distribution and shade in the area between your test statistic and the nearest tail. Then do the same for the other tail. So our test statistic was 1.31. It's roughly right about here. I'm going to shade in the area above it. So again, these are all the test statistics that are that extreme or more. Then I'm going to come over to negative 1.31. And these are test statistics that are just as extreme and more extreme on the other side of the distribution. Okay, and again, this total area, so it's had an area of 9.51%. So it had an area of 9.51%. And combined, and adding these up, that's again why we doubled it, you get a total area equal to 19.02%. All right, so next up, we've got to interpret these results. Okay, so step 4, interpret your result. You have a choice between the following two decisions. You can either reject the null hypothesis, we have evidence to suggest the die is not fair, or you don't reject the null hypothesis. We don't have enough evidence to suggest the die is not fair. So what do you think we should conclude about your die? So you've got to look at your p-value. Keep in mind, the smaller the p-value you have, the more evidence you have to suggest that the die is not fair. In other words, that you should reject the null hypothesis. So again, small p-values are rare if your null hypothesis is true. So in our case, it looks like we should not reject the null hypothesis. We don't have enough evidence to suggest the die is not. Right, so again, we're saying that we don't reject the null hypothesis. In other words, we don't have enough evidence to suggest the die is not fair. So a couple of things. Keep in mind, we're not proving the die is fair or unfair. We're just saying what is more likely given our evidence. And we don't accept the null hypothesis. We just fail to reject it. We're not proving the null hypothesis is true. We just have a lack of evidence to refute it. Not enough evidence to refute it. Okay. So these decisions are typically based on how small our p-value is. And the smaller the p-value, the stronger our evidence is against the null hypothesis. So how do we decide how small the p-value has to be in order to conclude that our die is not fair? We do this by choosing a significance level, and we use this symbol alpha, it's a Greek letter, to represent that. So remember, we were supposed to do this back in step 2 before we collected our data. Okay, we're returning to that now. So if our p-value is less than our significance level, and it's alpha, then we reject the null hypothesis. Most commonly used value is alpha equal to 0.05. So given this, should we reject the null hypothesis? That's another way of asking, is your p-value less than alpha? Is it less than 0.05? If we reject the null hypothesis, then we are saying that our results are statistically significant. So note that our p-value, double check this, that was 0.1902. You can flip back to double check. Notice that this is not less than 0.05. We were not below that cutoff, so we don't reject the null hypothesis, or we fail to reject the null hypothesis. In other words, our results were not statistically significant in this example. Okay, next bullet, is it possible that we could reject the null hypothesis even though the die is fair? What is the probability that we make this mistake? And last, is it possible that we could fail to reject the null hypothesis even though the die is not fair? Okay, so let's go back up to these one more time. So note again on that first one, our p-value was greater than alpha. And that 0.05 often is referred to as the power of the test. Okay. Second one, is it possible that we could reject the null hypothesis even though the die is fair? That's certainly possible. Right? The chance that that happens, or the probability that we make this mistake, is alpha. That's the 0.05 or 5%. And then the last one, is it possible that we could reject or fail to reject the null hypothesis even though the die is not fair? This again can happen. It's another possible mistake. So in this case, we can say yes, that's a possibility. As an example, to give you some numbers to think about. So we'll put a big if here. Oops, I'll get rid of that pop-up menu. So let's say that I had done another 60 rolls of the die, and I got 18 out of 60, or 0.3, or 30% of my rolls were 6s. Notice that this would have been more than 2 standard errors above the center. So I'm going to flip back to our graph so you can confirm this. So if I had gotten 0.3 or 30% of my rolls being 6s, it would have been in this region, somewhere in here, more than 2 standard errors above the center. Well, what does that mean? Go back down to here. In fact, if you were calculating this, you would find that your test statistic, or Z, would be 2.71. Kind of in that gray area. We're not really sure if you have enough evidence or you don't have enough evidence. Because if you take a look at the p-value, 2 times the probability that you get a Z-score greater than 2.71, you do 2 times 0.0034, which is 0.0068. That's below the cutoff. That says that we have enough evidence to reject the null and conclude that the die is probably not fair. But it could be fair. I mean, our distribution shows that this is a possible value. It's not a value that happens a lot, but it is a possible value. So that's where we want to be careful. We want to take a look at our significance level. And we want to keep in mind that we're not proving anything. We're just suggesting what's more likely given the evidence we have in front of us. And so again, with this particular example, even if we conclude that we're going to reject the null, that it looks like the die is not fair, it's still a possibility that we're wrong. The die could be fair, just that we're looking at an unusual or more rare result. Okay, here's one more example to illustrate the 4 steps in the hypothesis test. So of those women who are diagnosed to have early stage breast cancer, 1/3 will eventually die of the disease. Suppose a community public health department instituted a screening program to provide for the early detection of breast cancer and to increase the survival rate P of those diagnosed to have the disease. A random sample of 200 women was selected from among those who were periodically screened by the program and who eventually were diagnosed to have the disease. And so step 1, we're going to state a hypothesis about a population parameter, a claim about the world, and an alternative hypothesis. And we wish to detect whether the community screening program has been effective. So our null hypothesis, again, the status quo or prevailing viewpoint about a population parameter, and we're going to state the parameter of interest is equal to a specific value. So state this hypothesis in words and using symbols. So if we go back up, remember that our survival rate P, right here, let's see. We're told that 1/3 will eventually die of the disease. That means 2/3 is our survival rate. And so we come back down to our null hypothesis. We're going to say that the survival rate is 2/3. And in words, we're just saying that the survival rate stays the same, or is 2/3. Right. The alternative hypothesis, and as an alternative to the null hypothesis, is a change in the population parameter that the researcher hopes is true. So stating this hypothesis in words and using symbols, they're hoping that the survival rate increases. So we're hoping it's greater than 2/3. So in words, we're saying that the survival rate, again, either increases or is greater than 2/3. Okay, so remember these hypotheses need to be specified before the sample data are collected. Right, step 2, determine how you will use the data to make your decision and choose a significance level. So assuming the null hypothesis is true, can we use the central limit theorem to create a sampling distribution for the proportion of women who survive in a random sample of 200? So to answer this question, again, we need to check those conditions necessary for the central limit theorem. So is the sample random? Yes, I believe that was given to us. They told us it was a random sample of 200 women. And come back down. The observation's independent. I'm going to assume yes. The outcome of one female is different or independent of the others. Condition number 2, check our sample size. And our sample size is 200. Our hypothesized value is 2/3. And if we calculate this, we get roughly 133. If we do our sample size times 1 minus P, we get 1/3. And then again, times it by 200, we get roughly 67. Note both of these are greater than or equal to 10. So we can say yes, condition 2 has been met. And then number 3, condition number 3, is our population large enough? Is it at least 10 times bigger than our sample size? And so is the population size at least 2,000? I think we can say yes here. Okay, so continuing with step 2, choose a significance level alpha. Remember, we do this before we collect our data. So if our p-value is less than our significance level, alpha, then we reject the null hypothesis. So let's use a significance level that requires stronger evidence than our previous hypothesis test. So we're going to use alpha equal to 0.01. Remember, in our previous one, we used alpha equal to 0.05 when we were rolling the die. All right, so step 3, compute the observed value of the test statistic and compare your result to what the null hypothesis said you would get based on the sampling distribution for p hat. So since all 3 conditions for the central limit theorem have been met, we can create a model for the sampling distribution for p hat. So remember, we're assuming the null hypothesis is true until we have evidence to suggest otherwise. So the sampling distribution for p hat is approximately normal, with the mean or center at 2/3. And this is our hypothesized value. And has a standard error spread equal to, take 2/3 times 1 minus 2/3 of our sample size of 200. And that is roughly 0.033. So these are enough to help us complete the sketch of the following sampling distribution. So again, on our horizontal axes are all possible values for our sample proportion. They should be centered at 0.67. Going out 1, 2, and 3 standard deviations to the right. Just adding a standard error, adding 2 standard errors, and adding 3 standard errors. And then going over to the left, going 1, 2, and 3 standard errors below. And you should press pause and double check these numbers using a calculator. And now we've got an idea of what to expect if the null hypothesis is true. All right, so in our random sample of 200 women, 164 survived the disease. So this is enough information to calculate our sample proportion. So 164 out of 200 people, or 0.82, or 82%. Next up, we're going to use this to calculate our test statistic. This test statistic, again, compares the value of our p hat with the value that the null hypothesis says we should see in terms of standard units. So we're going to take our sample result minus the center of the distribution over the standard error. And the standard error was 0.033. And this gives us a test statistic of 4.55. Right, so let's go back up to our distribution and take a look at this. Our sample result of 0.82, notice, is off the chart. That's somewhere over here to the right. In fact, our test statistic confirms that it's 1, 2, 3, more than 4 standard errors to the right, about 4.5 standard errors to the right or above the mean. All right, so next step, calculate the probability of getting a sample result this extreme or more extreme. Again, this is referred to as a p-value. So notice in this case, our p-value is the probability of getting a p-hat as extreme or more extreme than our sample proportion. So we need to find the probability of getting a z-score greater than 4.55. And from our charts, off the chart, but we'll take the closest one there. It's 0.00, let's see, 1, 2, 3, 4, 5. There are 5 zeros there. So a very, very tiny p-value. Notice in this case, we're not doubling it. So again, the p-value is the probability, assuming the null hypothesis to be true, of obtaining a test statistic at least as extreme as the one actually observed. And extreme means in the direction of the alternative hypothesis. So our alternative hypothesis was that p was greater than 2/3. So notice that that sign matches this one. Okay. So since our alternative hypothesis did specify direction, we need to look at sample results that are as extreme as the one we found in just one tail of the standard normal distribution. And so let's mark the location of our test statistic on the following standard normal distribution and shade in the area between our test statistic and the appropriate tail. So we're roughly here. The amount of area to the right of that, underneath that distribution, is very, very tiny. So now we can interpret our results. Can we conclude that the community screening program was effective? Remember, you have the two choices. You have to make a choice between the following two decisions. One, either reject the null hypothesis, or two, don't reject the null hypothesis. So what should we conclude? So remember, we base our decision on how small our p-value is. Smaller the p-value, the stronger our evidence is against the null hypothesis. So should we reject the null hypothesis? Is our p-value less than alpha equal to 0.001? So our p-value, so make sure I get the right number of zeros, is definitely less than this significance level. So we should reject the null hypothesis. In other words, we have a statistically significant result. And this means that it's not likely to happen by chance alone. And so again, not likely to happen by chance alone if the null hypothesis is true. So is it possible we could reject the null hypothesis even though the community screening program was not effective? It is still possible. P-value is so little, the chance of that being the case is very small. And the second one, is it possible we could fail to reject the null hypothesis even though the community screening program was effective? And that's still a possibility.